Bismillahirrahmanirrahim. Hi everyone, I hope you are all doing well. My name is Azmat Ali and I welcome you all at my channel Academy of Mathematical Sciences. In today's lecture we will discuss problems 2.3 question number 16 to 18. I am using here the book Elementary Number Theory by David M. Burton. Lastly we covered up to question number 15. So let us start from question number 16. Question number 16 can be stated as given an odd integer a, establish that a square, a plus 2 whole square, a plus 4 whole square plus 1, this sum of 4 term is divisible by 12. As it is given that a is an odd integer, so let a is equal to 2n plus 1, where n is an integer. So substituting this a and a is equal to 2n plus 1 here, we get 2n plus 1 square. When you put a is equal to 2n plus 1 here, this becomes 2n plus 3. And lastly, when you substitute a is equal to 2n plus 1 here, this becomes 2n plus 5 whole square. Now we expand these three squares, and after summing all of the like terms, we have 12n square plus 36n plus 36. Taking 12 as a common, we have 12 into n square plus 3n plus 3, which is clearly divisible by 12 because this number is a multiple of 12. So it is clearly divisible by 12, which is required to prove. Question number 17. In this question, we need to show that 3n factorial over 3 factorial whole power n is an integer. We have to show this fraction is an integer for all non-negative integers n greater than or equal to 0. To prove, we use mathematical induction. When you put n is equal to 0 here, 3n factorial over 3 factorial whole power n, this becomes 3 into 0 factorial. As 3 factorial is equal to 6, this becomes 6 whole power 0. 3 into 0, 0, 0 factorial, 6 raised to power 0, this is 1. 0 factorial is 1, 1 over 1, this is equal to 1. And that is an integer. So the statement is true for n is equal to 0. We have to show this fraction is always an integer. So for n is equal to 0, this is equal to 1, and 1 is an integer. That's why the statement is true for n is equal to 0. Suppose that the statement is true for n is equal to k. It means when you put n is equal to k in the given question here, this should be equal to some integer. Suppose this fraction is equal to some integer q. See, this is our supposition, and we suppose this is equal to 1. We prove that the statement is true for n is equal to k plus 1. So consider the statement for n is equal to k plus 1 here. So when you put n is equal to k plus 1 in the given fraction, which is 3n factorial over 3 factorial whole power n. So substitute n is equal to k plus 1, we have 3 into k plus 1 whole factorial, 3 factorial whole power k plus 1. This can be written as 3k plus 3, and this 3 factorial is 6. This is equal to 6 whole power k plus 1. Breaking the factorial 3k plus 3 up to 3k factorial, this becomes 3k plus 3, 3k plus 2, 3k plus 1 into 3k factorial. This power can be break as 6 into 6 whole power k. Now by using 1, this fraction is equal to integer q. So replace this is equal to q. Now the remaining expression is after taking 3 common from here and cancelling that 3 with 6, we have 2 here. This becomes k plus 1, 3k plus 2, 3k plus 3. Say this is star. Now in star I have to show that this is an integer. Q is already an integer. So this fraction should be an integer. This fraction should be an integer. So we will discuss here two cases. Suppose if k is odd, because k is an integer, so it will be either it will be odd or even. So if k is odd, then clearly k plus 1 will be an even integer. So if k plus 1 is an even integer, then it will be divisible by 2. That is, k plus 1 over 2 is an integer. See here, if k plus 1 is an even integer, then you can divide it by 2. So if this fraction finally will be an integer. So in this case, when this portion k plus 1 over 2 is an integer, so this is an integer. 3k plus 2, 3k plus 1, this is also an integer for any value of k, either it is odd or even. So the final fraction becomes even an integer. Integer into integer is always an integer. So in this case, when k is odd, the star becomes an integer. If k is even, then 3k plus 2. 3k plus 2 is an even. If k is an even, you can take any even integer. Suppose my k is 4. Then 3k plus 2 becomes 3 into 4 plus 2, which is equal to 14. This is an even integer. So in this case, when k is even, then this number 3k plus 2 is an even integer. So by definition of even integer, it should be divisible by 2. So now 3k plus 2 is an 3k plus 2 over 2 is an integer. Hence, finally, star is an integer. So, okay. So the statement is true for n is equal to k plus 1, and whenever it is true for n is equal to k, hence by mathematical induction, the given statement is true for n greater than or equal to 0. This is an interesting question, question number 18, and this is also a long question. Prove that product of any 3 consecutive integer is always divisible by 6. The product of any 4 consecutive integer is always divisible by 24. And the product of any 5 consecutive integer is always divisible by 120. So we have to show product of 3, 4 and 5 consecutive integers. To prove the result, we will use the corollary 2 of theorem 2.4. What was the corollary of theorem 2.4? This can be stated as, if A divides C and B divides C, there are two numbers A and B, both divide C, such that the GCD of A and B are 1, that is A and B are relatively prime, then the product AB must divide C. This was the corollary, corollary 2 of theorem 2.4. So firstly, we show that the product of any 3 consecutive integer is divisible by 6. Let us suppose the 3 consecutive integers are a minus 1, a and a plus 1. So we show that 6 divide this product, a minus 1 into a plus 1. As we can write 6 is equal to 2 into 3, a number is divisible by 6 if it is divisible by 2 and 3, or we can use the corollary 2 of theorem 2.4 here. It is obvious that the product of any 3 consecutive integer is divisible by 3. I have to show that this product is divisible by 6. This is possible if it is divisible by 2 as well as 3. So I have written that it is obvious that product of any 3 consecutive integer is divisible by 3. You can take any 3 consecutive integers. It must be that one of them is a multiple of 3. Because among any 3 consecutive integer, it must be that one of the integer is exactly a multiple of 3. For example, you take 26 into 27 into 28. You can see here 27 is a multiple of 3. Suppose you start from 5 into 6 into 7. You can see here 6 is divisible by 3. So if you whenever you take any 3 consecutive integer, one of the integer must be divisible by 6 and divisible by 3. So this shows that the product of these 3 consecutive integer is divisible by 3. Mean to say 3 divides this product a minus 1 a into a plus 1. Next, I will show that this product is also divisible by 2. Next, if a is odd, then a plus 1 is an even integer. So it must be that this shows that 2 divides this product, because when a is odd, then a plus 1 is an even. If a plus 1 is even, then this whole product is even. So which shows this number is clearly divisible. This product is clearly divisible by 2. Similarly, if a is itself even, then there is nothing to prove 2 divides this product. So by using corollary, as 2 divide this product as well as 3 also divide this product, and the GCD of these two number 2 and 3 is equal to 1. So by using theorem 2.4, 6 divides the product of 3 consecutive integer. Next, we show that divisibility of 4 consecutive integer by 24. So firstly, I will break 24 into product of two integers such that their GCD should be equal to 1. Why am I not taking 24 as 6 into 4? If you break 24 in these two factors, you cannot use the corollary 2 of theorem 2.4, because that corollary says uh, the GCD of these two factors should be equal to 1. But you can notice that the GCD of these two factors, greatest common number that divides 6 and 4, is 2 here. So that's why I am not writing 24 is equal to 6 into 4. No, as well as not, we cannot write 24 as 2 into 12. If we want to use the corollary, it must be that you have to split 24 into such two factors which are relatively prime here. So 24 can be written as 3 into 8. Both are relatively prime because their GCD is 1. Next we let four consecutive integers such that a minus 1, a into a plus 1, a plus 3, a plus 2, sorry. So firstly I show that this product is divisible by 3 here. As in above part, we have shown that the product of first three consecutive integers is divisible by 3. So if this part is a multiple of 3, then clearly when you multiply this part with a plus 2, then it will be also multiple of 3. This shows 3 divides the product of these four consecutive integers. I repeat, suppose the product of these three consecutive integers, suppose this is equal to 24. This product has a value 24 and the next factor is 24 into a plus 2. Can I say that 3 divides this whole product? Yes, clearly 3 divides this product. So that's why whenever 3 divides three of them factors, then 3 clearly divides all of the 4 factors here. Next we show 8 also divides the product of these 4 consecutive integers. I have written it is obvious that 8 divides the product of these 4 consecutive integers. How? Case number 1. If a is an even integer, then a should be of the form a is equal to 2k here. So if you replace a is equal to 2k here, we have 2k minus 1 into 2k plus 1 into 2k plus 2. Taking 2 common from this bracket, we have that 2 into 2k, this becomes 4 into 2k minus 1, 2k plus 1, k into k plus 1. As for any integer k belong to z, this product k into k plus 1, this is always an even integer, because we know that the product of any two consecutive integer is always even. We have a result that product of any two consecutive integers is always an even integer. So here k and k plus 1 both are consecutive integer, that's why their product should be an even integer. Suppose their product is 2m. So when you replace this equal to 2m and after multiply 2m with 4, we have 8m into 2k minus 1, 2k plus 1. This shows that this number is multiple of 8, which is clearly divisible by 8. This is the first case when a is even. Suppose now if a is odd. If a is odd, then a should be of the form a is equal to 2k plus 1. So whenever you replace a is equal to 2k plus 1 in all factors, we have 2k plus 1, 2k plus 2, 2k plus 3. Okay. By taking 2 common from this bracket, we have 2 into 2k, 4k into k plus 1. This is 2k plus 1, 2k plus 3. Again, as k into k plus 1, this is the product of two consecutive integers, so it will be equal to 2m. Sorry, here will be 2m. So replacing k into k plus 1 with 2m, this become 8m. Clearly this number is a multiple of 8, hence 8 divides the product of 4 consecutive integer in both cases. So by using corollary, as 3 divides the product of four consecutive integer, as well as 8 divide the product of four consecutive integer. Finally, 24 divides the product of four consecutive integer with the property that their GCD is 1 here. Lastly, we show that 120 divides the product of these five consecutive integer. What is the first need? Firstly, we separate 120 into the product of two integers which are relatively prime. So I will write 120 as 24 into 5. I cannot write 120 as 12 into 10. So 120 can be written as 24 into 5 with the GCD of 24 and 5 is equal to 1. So now I have to show that the 5 divide the product of 5 consecutive integers. It is obvious that when you will take product of any 5 consecutive integer, one of them must be multiple of 5. So it is clear that 5 divides the product of any 5 consecutive integers. You can choose any 5 consecutive integer from anywhere. For example, you start from 67, 68, 69, 70, 71. You can see that which integer is divisible by 5. Clearly 70 is divisible by 5. So whenever you will take any product of any 5 consecutive integer, it is obvious that the product will always divisible by 5. Next target is to show this number is this product is also divisible by 24. Also, as 24 divide this number, 24 divide the product of 4 consecutive integer. We have shown this result in above part. So if 24 divide the product of 4 consecutive integer, it must be that 24 will divide the product of 5 consecutive integer. See here, as 24 divide the product of these 4 consecutive integers. So the product of this 4 consecutive integer will be a multiple of 24. So whenever this number is a multiple of 24, this is equal to suppose 24k. So when you multiply 24k with a minus 2, then the final product will always be divisible by 24. So we can say that if any 4 consecutive integer are divisible by 24, now if we multiply this product of 4 consecutive integer with another factor, fifth factor, then the product of that 5 consecutive integer will always divisible by 24. Hence, by corollary, we can say that 120 divide the product of these 5 consecutive integers. So, inshallah, in the next lecture, we will start from question number 19. If you find my videos helpful, kindly like, share, and subscribe my channel. See you in the next lecture. Take care. Allah Hafiz.